Very often radio signals reaching the receiver faces degradation due to multipath propagation, which reduces link capacity and link reliability. So, how do we cope with these degradation? Hello everyone, welcome back to the fundamentals of 4G. Today we will discuss how link performance is enhanced using spatial diversity. We will also discuss how spatial multiplexing is used in Mimo to enhance link efficiency. And finally we will discuss some futuristic technologies, such as antenna beamforming, which will dynamically serve the user to improve the coverage, and massive Mimo, which has the potential to increase the link capacity by several fold.
The principle of diversity is to provide the receiver with multiple versions of the same signal, which reduces the signal degradation considerably, and effectively improves the link performance. This can be done by time diversity, where same message is transmitted at different time slots; frequency diversity, where the same message is transmitted at different frequencies; and space diversity, it uses separate antennas, which are located in different positions to take advantage of the different radio paths that exist in a typical terrestrial environment. This concept is used in Mimo. Up until the 1990s, space diversity was used in systems that switched between two antennas, or combined the signals to provide the best signals. Such systems demanded high level of processing, but the system's processing were limited. However, with the improvement of processing power, it was possible to implement Mimo. Between a transmitter and a receiver, the signal can take many paths due to obstacles and objects in the medium. Traditionally, these multiple paths only introduced interference. By introduction of Mimo, these additional paths can be used to provide additional robustness to the radio link by spatial diversity, or to increase the link data capacity by spatial multiplexing.
So let us understand how both of them work in Mimo. Consider a system where a data stream 10111 is transmitted through a channel with deep fades. Due to fluctuation in the channel quality, the data stream may get lost or severely corrupted that the receiver cannot recover it. The solution to combat the rapid channel fluctuation is to add independent fading channels, by increasing the number of transmitting antennas or receiving antennas or both. So in brief, spatial diversity techniques, where same information is sent or received across independent channels to combat fading. Here diversity gain is defined as number of transmitting antenna into number of receiving antenna, which is equal to 1. Let us increase the number of receiving antennas by 1 count. The chances of proper delivery of the data across two link is very high. Thus, additional fading channel increases reliability of the overall transmission. Here diversity gain is 1 into 2, which is equal to 2. In this way, more diverse paths can be created by adding multiple antennas at transmitter side as well. The following figure shows a 2x2 Mimo system with number of diversity paths equal as to 2x2, which is equal to 4.
Now, as per Shannon's channel capacity theorem, there is a limit on the capacity of a channel for a given bandwidth. The capacity is also limited by the signal-to-noise ratio of the received signal. By using higher modulation scheme, we can certainly increase channel capacity, but for that, we have to have high signal-to-noise ratio. This trade-off can be difficult, expensive, and sometimes we cannot compromise.
Therefore, it is necessary to look at other ways of improving the data throughput for individual channels. Using spatial multiplexing, wireless communications can effectively utilize link capacity and spectral efficiency. In this technique, multiple antennas are used in transmitting and receiving, and each spatial channel carries independent information, thereby increasing the data rate of the system. This can be compared to orthogonal frequency division multiplexing technique, where different frequency subchannels carry different parts of the modulated data. But in spatial multiplexing, if the scattering by the environment is rich enough, several independent subchannels are created in the same allocated bandwidth. Thus the multiplexing gain comes at no additional cost on bandwidth or power. To recover the data stream at the receiver, it is necessary to perform a considerable amount of signal processing. First, the Mimo system decoder must estimate the individual channel transfer characteristic to determine the channel transfer matrix. Once all of this has been estimated, then the matrix H can be produced, and the transmitted data streams can be reconstructed by multiplying the received vector with the inverse of the transfer matrix.
This is how we can achieve link robustness using spatial diversity, and effective use of link capacity using spatial multiplexing. Apart from this, there can be many configurations in Mimo, and each one of them has specific advantage and disadvantage, such as single input, single output, single input, multiple output, multiple input, single output, multiple input, multiple output. These can be balanced to provide the optimum solution for any given application. After discussing all the aspects of Mimo, there are few more aspects which needs to be looked upon. Antenna beam forming. With the development of more adaptive systems and greater levels of processing power, it is possible to utilize antenna beam forming techniques with systems such as Mimo. In this technique, smart antennas are used, which can be of phased array system. Phased array systems have a number of predefined patterns. The required one is being switched according to the direction required. Adaptive array systems. This type of antenna uses what is termed as adaptive beam forming, and it has an infinite number of patterns and can be adjusted to the requirements in real time.
Now, traditional Mimo systems have 2, or 4, or 8 antennas. When number of antennas used in communication terminal are more than tens, or hundreds, then it is called massive Mimo system. The concept of massive Mimo or large Mimo systems is becoming popular as it is able to offer increased data rate, increased basic link signal to noise ratio, and channel hardening. Key issue which is faced in massive Mimo is antenna placement. As a rule of thumb, spacing of lambda by 2, where lambda is the wavelength of the signal, is considered necessary to provide almost no correlation between the antennas. And in order to achieve this, various approaches can be taken, such as use of higher frequencies, use of volumetric spacing, and use of spatial modulation. One of the key requirements for a large Mimo system is rich diversity of signal paths between the transmitter and receiver. This is normally present within a typical indoor and most urban environments. Other environments where there are less paths won't be able to provide the same benefits with a Mimo or large Mimo system.
So friends, in this brief video on Mimo we have seen how multiple path increases link robustness and spatial diversity, and link capacity and spatial multiplexing. We have also seen how in future, coverage can be improved using antenna beam forming, and throughput can be enhanced using massive Mimo. In our next video on carrier aggregation technique, we will discuss how throughput is enhanced by combining multiple bands. You can post your doubts in the comments section. Don't forget to share it with your friends. Happy learning!